In today's lecture, we are going to begin with the topic equilibrium of bodies. So, when is a body said to be in equilibrium? When a number of forces acting on the body produce no change in its state of rest or of linear or rotational motion the body is said to be in the state of equilibrium. So basically there are a number of forces acting on a body and it produces no change in its state of rest or motion. Motion can be linear or rotational. The body is said to be in equilibrium. Like consider the notebook. So this notebook has some weight and the weight is acting vertically downwards. What happens is this table on which the book is kept pushes this book with a force equal to that of its weight in the upward direction. So the weight of the book downwards on the table, same amount of force is acted by the table on the book. So they cancel out each other and the book is in a state of equilibrium. Since this book is in a state of rest, this type of equilibrium is called static equilibrium. So now let's discuss the kinds of equilibrium that we see. Of which first one is the static equilibrium. When a body remains in a state of rest, under the influence of several forces, the body is in static equilibrium. So example number 1. If a book is lying on table, the weight of the book exerted on the table vertically downwards is balanced by an equal and opposite force of reaction exerted by the table on the book vertically upwards. Thus the book is in static equilibrium. Second example, in a beam balance, what happens is, suppose when you weigh your vegetables, when you buy vegetables, so one side what we have are the stones, the weight stones, say there is 1 kg stone, and the other side what we do is we place vegetables equivalent to 1 kg. So when the left hand side has 1 kg and the right hand side where we kept the tomatoes also have 1 kg, what happens is the beam balance comes in static equilibrium. It comes to a position of rest. It rests horizontally. So that is also an example of static equilibrium. So in a beam balance, when the beam is balanced, in a horizontal position, the clockwise moment of force due to the object on the right pan balance is the anti-clockwise moment of force due to weights on its left pan, and the beam has no rotation, and the beam has no rotation or rotational motion. That is, it is in static equilibrium. Second kind of equilibrium is the dynamic equilibrium. As the word suggests, this equilibrium is of the body when the body is in linear or rotational motion. It does not changes its motion, it remains as it was moving. So that is our dynamic equilibrium. So when a body remains in the state of motion, be it translational or rotational, under the influence of several forces, the body is said to be in dynamic equilibrium. Okay, examples. Number 1, a raindrop reaches the earth surface with a constant velocity. Okay. This is our indication that whenever anything falls down, what happens is it accelerates. It increases its velocity due to the acceleration due to gravity. But in case of a raindrop, or whatever acceleration is produced downwards, whatever force is there downwards, is balanced by the upward force. Let's see how. The weight of the falling drop is balanced by the sum of the buoyant force and the force due to friction or viscosity of air. Thus, the net force on the drop is 0. So, it falls down with a constant velocity. Okay, so one word we see, that is the buoyant force. So what is the buoyant force? Buoyant force is nothing but the upthrust. Whenever you take a mug, say, and you invert it and try to put it inside water, you will feel a certain force that is being exerted upwards due to the air column that is present inside the mug. So that force is called the buoyant force or the upthrust. Whenever water comes down through the atmosphere, what happens is it experiences the same force upwards, and the other force is because of friction. And air also has friction. To explain this, you can take example of a badminton. Whenever you try and hit the shuttle very tightly, what happens is the air swishes. You hear a swishing sound of the air. That swishing sound of the air is nothing but because of the friction that is present in the air. So because of the buoyant force and the friction that is there in the air, what happens is it experiences a force upwards that is equals to the weight of the falling drop, which is downwards. So as they are balanced, what happens is a raindrop falls with a constant velocity downwards. And second example, a stone tied at the end of a string when whirled in a circular path with uniform speed is in dynamic equilibrium because the tension in the string provides the centripetal force required for circular motion. Okay, so we come across a term called centripetal force. Centripetal force is basically a force acting on a body towards the center. Centri means center, petal means towards. Center seeking force is basically the centripetal force. Say you sit in a merry-go-round. So whenever you move around in a merry-go-round, what keeps you intact in the merry-go-round is the string or the iron rod that is attached to the center that keeps moving. So that is how we keep attached to the merry-go-round. That is the centripetal force that we are getting. So whenever a string is wound around in a wire and you move the wire, what happens is the wire provides the necessary tension, and this tension provides the centripetal force, that is the force that acts towards the center. And say when you sit in a merry-go-round and the merry-go-round goes round and round, what happens is you feel a force that pushes you outwards. So that outward force that you feel is called the centrifugal force. We'll come to that in the third section properly. But that force is called the centrifugal force, and this centripetal force and centrifugal force, when they are equal, a body is said to be in dynamic equilibrium and the body keeps on moving with a uniform speed in a circular motion. So this is our second example for dynamic equilibrium. Inward force, centripetal force experienced by the tension, and outward force, centrifugal force, that is what you feel. That is not actually present, that is not a real force, that is something that an object feels. Okay, so with this we come to conditions for equilibrium. So there are two conditions. First condition is that the resultant of all the forces on the body should be 0. So this works perfectly fine for a static equilibrium or dynamic equilibrium in translation motion. But for rotational motion, we define a second condition, that the algebraic sum of moment of all the forces acting on the body about the point of rotation should be 0. There should be no clockwise, the resultant should have no clockwise or anti-clockwise, it should always be 0. Only then we say that the body is in equilibrium. So with the help of second condition, what we generate is a principle of moments. And this principle of moments is important for your syllabus. From principle of moment itself we get numericals. So according to the principle of moments, in equilibrium, sum of anti-clockwise moments is equals to the sum of clockwise moments. So this is our principle of moments. Next, the verification of the principle of moments. To verify this, we use a meter rule. So suspend a meter rule horizontally from a fixed support by means of a strong thread at O. Okay, let's draw the figure for this one. So we are taking a uniform meter rule Why am I making this marking is because a uniform meter rule consists of 100 centimeter. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So this becomes a uniform meter rule. So obviously to support and held it horizontally, the thread must be connected at the center of this uniform meter rule. So it is connected to a rigid support. And this point is our O. Next, what we are doing is we suspend some slotted weights W1 and W2 on either side of the thread in such a way that the meter rule remains horizontal. So if we suspend any weight, say if we suspend one weight over here, so this body will start moving in the clockwise direction. So what we do is we put it on either side, one on the right side, one on the left side. So one results in the clockwise movement, another results in the anti-clockwise movement. So overall what happens is the clockwise movement and the anti-clockwise movement, they cancel out each other and the resultant body is in equilibrium. So let the weight suspended from the spring balance A on the right side of the thread be W1 at a distance OA equals to L1. So we are naming the distance A as L1. While the weight suspended from the spring balance B on the left side of the thread B W2 at a distance OB equals to L2. So what are we doing is we are basically, say this is point A, we are taking a spring balance over here and we are suspending some weight, that is W1. This weight is W1 and this length OA is equals to L1 we are taking. Now say we are taking another weight, say W2, and this point is B and the length of this OB is L2. So because of W1, what happens is this meter rule starts moving in the clockwise direction. So clockwise moment of weight W1 about the point O is equals to W1 into L1, and anti-clockwise moment of weights W2 about the point O is equals to W2 into L2. Because O acts like a pivot over here, this body moves about O. Keeping O fixed, this body will move about O. Therefore, we are checking the distance from the point O. So now at the end we saw that we adjusted it in such a way that the meter rule remains horizontal, means the body is at equilibrium. So in equilibrium, when the meter rule is horizontal, it is found that W1 into L1 is equals to W2 into L2. That is, the sum of our clockwise movement is equals to the sum of anti-clockwise movements. So that is, clockwise movement is equals to anti-clockwise movement. So this verifies the principle of moments. Okay, W1 tends to move this meter rule in the clockwise and W2 tends to move this in the anti-clockwise. They cancel out each other. Now let's discuss some numericals relating them. First example, the iron door of a building is 3 meters broad It can be opened by applying a force of 100 Newton, normally at the middle of the door. Calculate number A, the torque needed to open the door, and number B, the least force and its point of application to open the door. Okay, so for this given force is 100 Newton. We are solving part A, and the distance of point of application of force R is half of the breadth of door. Why so? Is because this force was applied in the middle of the door. So it will become half of the breadth of the door. So if say the breadth of the door is 3 meter, we are applying force at 3 by 2 meters, which is equals to half into 3, which is equals to 1.5 meters. Therefore, torque needed to open the door is equals to the force into the perpendicular distance, which will be equals to 5, that is 150 Newton meter. And part B. Part B, what did they ask is the least force and its point of application to open the door. Okay, so we have already seen that in the previous class. Here, when we were doing examples of moment of force, we concluded that larger the perpendicular distance, less is the force needed to produce the same turning effect. So the turning effect or the torque that we need is this much, 150 Newton meter. So if the larger perpendicular distance is there, then the force required will be less. So on the door, where will we be applying the force is at the hinge, at the distance maximum from the hinge, that is at a point where the handle is placed. So when we apply a force over here at the maximum perpendicular distance from the axis of rotation, what happens is the force needed is the least. So the force required will be the least. If it is applied at the farthest point from the hinges. Let the force required be F dash Then moment of force is basically torque is equals to F dash into 3, because the maximum distance will become 3, that is the breadth of the door, which implies moment of force. We found out the least moment of force is 150, which is equals to F dash into 3, which implies F dash is equals to 150 by 3, which is equals to 50 newtons. So the minimum force that will be required to open the door is 50 newton. Example 2. The wheel shown in the diagram below has a fixed axle passing through O. The wheel is kept stationary under the action of number 1, a horizontal force, F1 at A, and number 2, a vertical force, F2 at B. So part A that we need to find is to show that the direction of force F2 in the diagram. Number B, which of the force F1 or F2 is greater, and number C, find the ratio between the forces F1 and F2 given AO is equals to 2.5 centimeter, BO dash is equals to 1.5 centimeter, and O dash O is equals to 2.0 centimeter. Okay, so let's draw the diagram. Say we took this circle, this is O, this point is A. We are applying a horizontal force F1 on A, and this line given here is the O dash B. So we need to apply a vertical force at B such that this body becomes at equilibrium. Okay, so solution part A. So we need to show the direction of force F2 in the diagram. The force F1, see this is our fixed point, O is the fixed point, that is the pivot. So this force makes this body move in the clockwise direction. So the force F1 applied at A produces a clockwise movement on the wheel. So, we apply a force F2 vertically downwards in order. So this was a vertical force. If you would have applied this upwards, this would still make this body rotate in clockwise. So clockwise plus clockwise would make this body completely move in the clockwise direction. But the body needs to be stationary. In order to make this body stationary, what we are doing is we are applying this force F2 in the vertically downward direction. So by applying this force F2 in the vertically downwards direction, remember that this is a part of the solution. You need to redraw the diagram and you need to show this force F2 acting vertically downwards. So F1 is resulting in the clockwise movement. F2, if you were to apply it vertically downwards, this moves the wheel in the anti-clockwise. So they will ultimately cancel each other out to keep the body stationary. So we apply the force F2 vertically downwards in order to produce anti-clockwise movement which balances the clockwise movement produced by F1. Part B. Which of the force F1 or F2 is greater? Okay, so coming back again to this one. So here we concluded for moment of force that the larger the perpendicular distance, less is the force needed to produce the same turning effect. So this is our perpendicular force. So the distance, perpendicular distance is OO dash. OO dash is 2 centimeter, and for F1 the perpendicular distance is OA. OA is 2.5 centimeter. So whenever the perpendicular distance is larger, the force needed will be smaller, and whenever the distance will be smaller, perpendicular distance is smaller, the force needed will be larger. Therefore, from this we conclude that since the perpendicular distance OA of point of application of force F1 from O is greater than the perpendicular distance O dash of point of application of force F2 from O. So F2 is greater than F1. Wherever the perpendicular distance is smaller, the force required will be larger, and perpendicular distance is larger, the force required will be smaller. So F2 is greater than F1. Do note over here that this F2, we are not taking OB as the perpendicular distance. This is the direction of force. So the perpendicular distance should be perpendicular to the force. If this is the force, direction of the force being applied, So the perpendicular distance to this direction of force is OO dash. So we are taking OO dash as the perpendicular distance, not BO dash. It is OO dash. Okay. And the third part, find the ratio between the forces F1 and F2, and this is given to us. For part C now, moment of force F1 about O is equals to F1 into OA, which produces clockwise moment, and moment of force F2 about O is equals to F2 into OO dash, which produces anti-clockwise moment. So according to the principle of levers, in equilibrium, clockwise movement is equals to anti-clockwise movement. I am not writing sum of clockwise movement because there is just one clockwise movement and one anti-clockwise movement, is equals to anti-clockwise moment. So this implies clockwise movement is F1 into OA is equals to anti-clockwise is F2 into OO dash. So F1 by F2 is equals to OO dash by OA. So OO dash given to us is 2 and OA or AO given to us is 2.5. So 2 by 2.5, decimals cancel off. So 20 by 25 is 4, 5 fours are 20, 5 fives are 25. So this is 4 by 5. So therefore F1 is to F2 is equals to 4 is to 5. This is our ratio. Okay, and the third example and the last example that we are going to deal with is a uniform meter rule rests horizontally on a knife edge at the 60 centimeter mark. When a mass of 10 gram is suspended from one end. Draw the diagram of the arrangement. Number A, at which end must this mass be suspended? And number B, what is the mass of the rule and number C, the 10 gram mass is now shifted to 90 centimeter mark, in which direction must the knife edge be shifted to make the rule horizontal again. Okay, solution. So first of all, what we are doing is the drawing of the arrangement that is given to us. So we'll mark 10 centimeter of length we are taking 10 because it is easy to mark 10, 20, 30, 40, 50, 60, 70, 80 and 90, and the last one becomes 100. First one is 0. So this is our uniform meter rule, where this mark is 0 and this mark is 100. Now it's given that a knife edge is placed at a 60 centimeter mark. So 10, 20, 30, 40, 50, 60. So this becomes our knife edge. This is our pivot. Let's mark this as O. So when a mass of 10 gram is suspended from one end, so this meter rule that we took also has some mass, and the mass of this whole meter rule will act at the center of the body. This is called the center of gravity, and this will bring it downwards because weight always acts in the downward direction. See, the mass of rule be capital M, so this brings mg, and this results in the movement of the rule in the anti-clockwise direction. So we'll place it at the other end, that is at the 100 centimeter mark, a mass of 10 g, so that this produces a clockwise movement such that this anti-clockwise and the clockwise this get cancelled off. We are marking this whole meter rule as AB. So the above figure part A, the above figure shows a uniform meter rule AB rests horizontally on the knife edge at O. This is our 60 centimeter mark. Let capital M, this we are taking as the mass, gram, be the mass of the rule. This g is the acceleration due to gravity. Here, instead of writing just g, I wrote the gram so that you do not get confused. M grams be the mass of the rule. So the weight N into g, this g is the acceleration due to gravity. Weight is mass into the acceleration due to gravity, acts at the middle point that is at 50 centimeter mark. the weight mg of the rule produces, and this is producing an anti-clockwise movement. So the 10 gram mass, this G is gram, so 10 gram mass must be subtended at end B, that is at 100 centimeter mark, because we need this in equilibrium. If we place this 10 gram also over here, what happens is this is also producing anti-clockwise, this will also produce anti-clockwise. This whole rule will start moving in the anti-clockwise direction. That is why if one is producing anti-clockwise, the other must produce clockwise. So we are placing this 10 gram weight at 100 centimeter mark to produce clockwise moment about O. Okay, so first part done. For the second part, it is asking what should be the mass of the rule. This we can easily find using the principle of levers. So according to the principle of levers, anti-clockwise moment is equals to the clockwise moment. Okay. While we verified this, while we wrote this down, we wrote sum of anti-clockwise movement as the sum of clockwise movements. But since here there is only one clockwise and one anti-clockwise, it is not important to write sum of. Okay. And sorry, this is the principle of moments, not principle of levers, principle of moments. Anti-clockwise moment is equals to the clockwise moment. So which implies anti-clockwise moment is produced by our weight of this ruler, which is producing mg weight into the distance from the pivot will become 60 minus 50. Because 60 is at the pivot and at 50 this mg is the mass of the ruler axe, so this distance will be 60 minus 50, that is 10, and clockwise movement will become 10 g is acceleration due to gravity, into distance from the pivot. This distance is at 100 mark, this is at 60 mark, so the distance will become 100 minus 60. G and G cancels off. So M into 10 is equals to 10 into 40. So which implies M is equals to 40 grams. So this 10 and 10 cancel off. So mass of the ruler is basically 40 gram. This G is gram. Please do not get confused. This G we used over here was a force, the weight of the ruler. That's why we used acceleration due to gravity. The last mass that we are getting, this G represents the unit gram of the ruler. And part C. So the 10 gram mass is now shifted to 90 centimeter mark. In which direction should the knife edge be shifted to make the rule horizontal again? So what happens if we place it at 90 centimeter mark is the perpendicular distance decreases. So if perpendicular distance decreases, the moment also decreases. So if the moment about the clockwise direction decreases, the anti-clockwise direction is more. So which will produce a movement in the anti-clockwise direction. So what we need to do is we need to decrease this perpendicular distance. So if we place this knife a little left what will happen is this perpendicular distance decreases and this perpendicular distance will increase. So with this decrease in perpendicular distance, the anti-clockwise movement will decrease, and with the increase in the perpendicular distance here, the clockwise movement will increase. So we'll shift this such that they become equal, and hence it becomes an equilibrium. So how do we write this? So when the 10 gram mass is shifted to 90 centimeter mark, its distance from the knife edge reduces resulting in decrease of clockwise movement. So the knife edge must be shifted away from the 10 gram mass to reduce the distance between the knife edge and mass M, so as to make anti-clockwise movement by capital M equal to the clockwise movement by 10 gram mass that was shifted. With this, we come to the end of this lecture. Please practice all the numericals from the first exercise which are relating these examples that we solved. Thank you.